and welcome to another edition of New England Authors. So good to have you here. We're going to talk science today, and our guest is Graham Farmelo. Graham, welcome to the show.
My pleasure.
Did you hear that? He is not from New England, he's from Old England.
The real England.
The real England, okay. And in fact, a science writer, written several books, and a fellow at the University of Cambridge in England.
The real Cambridge.
The real Cambridge. And we're here in Cambridge, Massachusetts, and we broadcast on stations throughout New England. And you're also an adjunct professor of physics at Northeastern and a former director of the London Science Museum in South Kensington, one of my favorite places. I really recommend that. They have a great place for Darwin. So your latest book is The Universe Speaks in Numbers, but before we start talking about that, I'd like to talk about a couple of your other books.
Sure.
One is a biography of Paul Dirac.
Yep.
Now, he's not a household name, but very important to physics. Can you tell us a little about him?
Yeah. His nickname, so to speak, is the British Einstein. Dirac was a really great physicist. He was one of the people who pioneered the most revolutionary theory of the 20th century, which is quantum mechanics, the theory of matter at the atomic level, which behaves completely differently to everyday matter.
Yeah.
Now, Dirac was a pretty singular person, very quiet, a person of very, very few words, but a very deep thinker. And among his contributions, he deduced by pure reason, so to speak, the existence of antimatter, the flip side of matter. Now, cosmologists today believe that in the very early universe, matter and antimatter were in equal amounts. Right. So you can think that Dirac conceived half the early universe in his head. I mean, he was a very, very deep thinker.
Yeah, and he came up with a unique theory of the electron.
That's where he got that from. That's right, yeah. And he used Einstein's theory of relativity, the basic theory, and quantum mechanics. He pushed them together, and from that he got the only equation until recently in Westminster Abbey, which describes the electron.
Yeah.
And it was from that equation that he deduced the existence of antimatter.
So in his theory, everything that was like an electron, there's an opposite one called a positron, right? Yeah. And every one has this.
That's right. Technically, every particle that has is like an electron has the same type of spin that has antimatter. And we now know that every basic particle has a flip particle, so to speak, antimatter. So this was his friend and rival Werner Heisenberg said the realization of that was the biggest leap forward of all the leaps forward in 20th century physics, which is some going for a rival to say that.
Yeah, so in your biography, you talk about Heisenberg and Einstein and Niels Bohr and all these great thinkers of the earlier part of it. But you said he was a silent guy. He was emotionally traumatized, right? Can you talk about that a little?
Well, yeah, there was something not quite normal about his personality. I think most people would say that.
The biography, in fact, is called The Strangest Man.
Yes, Niels Bohr said that Dirac was the strangest man he ever saw at an institute, which by the standards of theoretical physics is some going. People at the time defined the Dirac as 1 word per hour. I mean, it was a kind of new unit. He was really, he was very, very sparing with words. And when he was in Copenhagen, it was said that he only had 3 phrases: yes, no, and I don't mind. I mean, everything else was too frivolous for him, you see. Dirac said that the reason why he was a person of so few words because he was so terrified of his father at the breakfast table, because his father would chastise him if he said 1 word that was incorrect, because they spoke only French. And he said this drove him into this almost wordless state. Most people, I think this is very unlikely, and I conjecture in the book that he was probably, as we would now say, on the spectrum. You can't prove that, but it looks very much like that from his behavior.
Well, he did have a very dominating father, and that drove his brother to suicide, right?
Well, that of course is a matter of conjecture, but certainly his brother was very unhappy. Their childhood, according to Paul Dirac, was a very unhappy one, and his brother, who was nothing like as bright as him, they were even estranged in their teenage years.
Yeah.
So it was a terrible trauma for Paul Dirac when he was a graduate student. He heard that his brother had killed himself because he had never made his peace with his brother.
Yeah, well, we could talk a lot about this, but I do want to move on to your other book, Churchills Bomb. So a British scientist, a German scientist, everybody knew that the atom bomb was possible. And the British scientists started working on it before American scientists, right? And then what happened?
Well, you say that everyone knew it was possible. I mean, nuclear fission, the breaking up of atomic nuclei, the particles, the core of atomic of atoms. That was first done right on the eve of the Second World War, and this was, if you like, one of the great acts of fate of the 20th century, because human beings found out how to release this potentially huge store of energy right before what was going to be the biggest conflict in human history, right? So this was an extraordinary thing to happen. But what they didn't know, what scientists didn't know, was how to harness that energy in the form of a bomb, for example. And the first people who we know hit on the idea of how to do that were Rudolf Piles and Otto Frisch in Birmingham. And that realization took place in March 1940, just before Churchill became Prime Minister. Yeah. So in Britain, a group of scientists, particularly physicists, understood a method, which we could talk about if you wish, of how you might in principle build a bomb. And the British scientists had a head start on this, but they didn't have the backing from the government or indeed the facilities to build a bomb. And what happened was that when the Americans got into the Second World War after
Pearl Harbor.
They got into it in a big way, and then the British looked like Johnny come lately, so to speak, because they joined the Manhattan Project, and the project was very much then an American one, and that was an incredible achievement in a sense, to have built a bomb so quickly during the Second World War.
Yeah. So initially, Churchill was favored trying to find out if the bomb is possible,
yes,
and then he got some bad advice.
Yeah,
about it.
Yeah, you're right. He was very proud of this later on, because he was someone who didn't like. He wanted to make sure that his best side was presented to future generations. I mean, for me, in writing the book, what was truly extraordinary was that even in the 1920s, Churchill was interested in quantum mechanics. This is a politician, a leading politician. I mean, 1926, he was a major politician in Britain, and instead of working on the budget, the biggest event of the year, he was writing notes on quantum mechanics. Now, this is extraordinary, right? In the early 1930s, when British scientists in Cambridge were doing pioneering research into nuclear physics, just a year later, he was chairing a meeting about those findings. So this is an unusual politician, because he wasn't a talented scientist, but he was interested in science. And what I demonstrate in Churchill's Bomb is that he was incredibly well prepared for these nuclear developments. But things, we're in the fog of war, in the Second World War, and I don't think all his decisions were that great when it came to it. But that said, he was under enormous pressure because he was leading his country and its empire during the war years.
Yeah. It would be interesting to speculate what happened if the bomb came before Germany surrendered.
Oh, well,
something.
that's so much fruit for novelists as well, of course, yeah.
All right, so this is, by the way, this is New England Authors, and we're speaking with Graham Farmelo, a great science writer. So your latest book, The Universe Speaks in Numbers, you argue that mathematics and physics should be one discipline, and that you can't have one without the other. Is that a fair
Well, that's a very optimistic reading of my conclusion. If I just unpack it slightly, if I may.
All right.
The first thing to say is that mathematics and physics are, in principle, different. Physicists are about trying to understand the real world, the world in which we live. They're trying to understand the observations we make on it, the measurements that you make on it, in laboratories and what have you. Mathematicians, on the other hand, they work, you could imagine them working in a darkened room, so to speak, with their webs of ideas, right, which are not about the real world necessarily, but just purely abstract. Mm-hmm. Now, as Einstein said, the miracle, as he put it, of our universe is that it has an underlying simplicity. You wouldn't guess that from looking at the great constellations, right to all the territory in our galaxy and on Earth here. But underneath that are a relatively small number of laws through which we can understand the universe. Now the point is, as Newton taught us, those laws are written in mathematics. Now, what we now see is that the workings of these mathematicians who aren't thinking about the universe are directly relevant to the physicist trying to understand the pattern in our universe. And these days, as we speak here in the beginning of the 21st century, it seems that more and more the pure mathematicians and physicists are being driven towards the same goal. Now, this is a quite remarkable development, right, whereby physicists are really getting to the deepest questions in the universe in collaboration with these mathematicians.
Yeah. So you begin with delving into the history of science from the ancient Greeks. And you mentioned Pythagoras kind of in passing, but Pythagoras' whole school was about numbers and geometric geometric forms and so on.
This is true. Well, I mean, we're all indebted to the ancient Greeks, and Isaac Newton, who was the first person in 1687 in his Principia Mathematica, who set out the idea that we need to understand the universe in terms of basic laws written in mathematics. Right. But he knew he was standing on the shoulders of great thinkers all the way back to the ancient Greeks. Right? And their insights are still valuable to this day. Mm-hmm. They weren't, of course, right in every detail. In some ways, they got things completely wrong, but they really did get the ball rolling.
Yeah, Aristotle got a lot of things right as well.
I think he had a lot of physics right. I mean, but he was, year by year, probably the most influential thinker in human history about the natural world. Right. But he was wrong about very wrong about one thing, because he thought there was no fundamental reason why mathematics should be able to teach us about the nature of the universe. He knew you could apply it to technological things and what have you, but he didn't think it had a fundamental role in understanding the universe. Now, that's simply not true. We know that mathematics is a deep part of our understanding of the universe.
So why did you come out with this book now? Or is there some current scientific breakthroughs, such as this powerful accelerator in Switzerland?
Well, there's a reason for it. First of all, as I said, mathematicians and physicists are now working together incredibly closely. That hasn't always been the case. Mm-hmm. After the Second World War, there was what Freeman Dyson calls a divorce, where they had nothing to do with each other, very little to do with each other. But more recently, they've come together and found common cause, so to speak. I got interested in this subject because when I was a student, I thought this very mathematical approach to the universe was, the universe can't be that complicated. I thought it was much better to concentrate on experiments and look at what nature is telling us and try to abstract ideas from that. Now, what happened was, in the early 1970s, it was a wonderful party. Experimenters and theoreticians were working together. It was terrific. But since in the last 20 or 30 years, that flow of new insights from nature has largely dried up. There have been a couple of great insights, but not nearly so many. So that's why we've gone back to the thinking of Einstein and Paul Dirac, who believed that by looking at the mathematical content of our best theories, you could find a way forward. And that's the kind of thinking that is used today in some parts of the frontiers of physics.
So could I ask you an off-the-wall question?
Sure.
So there have been these great theories. Have they improved our lives?
Well, I think they've improved it in that it gives us a clearer sense, an understanding of the universe in which we live. Now, I think that's something important. I mean, I don't think the just bit getting richer or even getting happier is the only thing about, that makes life worthwhile.
Right.
There is something about understanding this extraordinary environment in which we live, and what these scientists are doing is helping us to refine our understanding of the entire universe, of the nature of space, the nature of time, the really deepest questions about this universe in which we find ourselves. I think that's important.
Yeah, so maybe we're appreciating the universe more. We're
Yeah.
appreciating our role and our place in it.
It does distinguish us from people who all they want to do is, make money or just have fun or just exist by just eating or what have you. You know, this is about something that transcends the everyday, so to speak, and the necessary parts of just living. This is about understanding what we have, the environment in which we find ourselves.
So if you're just joining us, this is New England Authors, and we're talking with Graham Farmelo. So math and physics are orderly. They're logical disciplines. You tell us that it's not possible to understand what it's all about, the nature of the universe, via order and logic, right? We need observation. Isn't observation also limited because it's human sight and data and...
Well, what I would say is that yes, mathematics has a very important role in this story, but as Newton taught us, in the end you've got to compare the best theories that you have with the most accurate observations that we have. Now, there is a limitation on observation, as you know, quantum mechanics has demonstrated that, but nonetheless it is still possible to take the most precise observations that we can and compare those observations with the predictions of experiment. And that still is the gold standard of theory, and that, in my opinion, must always be the case. In the end, physicists are trying to understand the natural world, and their theories must be checked constantly against those measurements.
So in our telescopes and our understanding of the universe more, are we getting a better picture of it? I mean, it was just only 20 years ago that we came up with the idea that the universe is not only expanding, it's expanding faster and faster and faster.
That was an extraordinary observation.
Yeah.
I mean, still, I meet physicists today who say to explain that is above my pay grade. You know, that is an incredibly difficult, because everyone was expecting that expansion would be slowing down, if anything. I mean, what would make it go faster? Right? If you look at a back of the envelope calculation of the best theories that we have, a simple observation that looks at that expansion, it's out by 120 orders of magnitude, and that shows we are really missing something here.
Yeah.
To understand that observation, which a Nobel Prize-winning observation, rightly so, we really have got a lot of thinking to do. So there's a lot of room for humility among physicists here.
Yeah, there is. And one of the things I think that science tries, a lot of times science is accused of trying to understand the mechanics, but not the questions of, what came before the Big Bang? What's this? Why are we here? What's this life all about? Do you think that's true, or could we understand that through science?
It would be a very it would not be wise for me to say we will never understand this or that. But to me, in all humility, I mean, to understand before the Big Bang, that seems to me a bit of a stretch. I'm quite content to understand right the way back to the origins of time, which is our current understanding of the beginning of the universe. That's when time and space began. I mean, I should say one thing, that the best theory that we have now for understanding the most basic forces of nature, that's string theory, that lives most naturally at extremely high energies, which are very difficult to access. And that's why it's so difficult to test that theory, and that's a real challenge for theoreticians these days.
There's a lot of optimism in your book. Who did you interview?
Well, it might be quicker to say who I didn't interview. No, I interviewed a lot of people at the Institute for Advanced Study, where I'm spending this summer. They have some fantastic physicists there, the counterparts of your Einsteins and Diracs and Heisenbergs and what have you. But also here at Harvard, my home university of Cambridge, the Institute for Theoretical Physics in Santa Barbara. I mean, and at CERN, indeed, I spoke to a lot of experimenters as well. You know,
CERN is the
atom smasher, the highest energy atom smasher we've ever produced. That's right. And I tried to get all sides of this question, but that said, I presented my view, which I hope is a rational one. I don't say that you know, everything's hunky dory and that we can just go ahead with the mathematics as if there were no problem. But I do think it reasonable to say that physicists appear to be on a very promising line at the moment, guided by observation and mathematics.
So the two big physics theories are quantum mechanics and relativity.
Yeah, that's right.
Are they in conflict with each other?
Well, they look like it. Yeah, as you say, quantum mechanics was the most revolutionary theory of the 20th century. Einstein was never comfortable with it. He admired it for its predictive ability, but he never felt comfortable with it. And the other one was the basic theory of relativity, which was a modification of Newton's idea of space and time, namely that they were absolutes. Now, Einstein, among many others, thought it was going to be impossible to combine those theories. They look completely different when you see them on a page, mathematically. But it has been possible through something called quantum field theory to jam those things together. It's very, very difficult to do, extremely difficult to do, but nature seems to insist on both theories. And that quantum field theory has been extremely well checked in the laboratory. Now, the theories that we're now building are all based on those two theories. And that's what keeps them grounded in reality. And that's what is so exciting about them, in my opinion.
Oh, that's great. Okay. So, talk about the search for a unified field theory. This was something that was supposed to integrate gravity into these theories.
Yeah.
Einstein was very frustrated. Is there still interest in that among physicists?
Absolutely. This is the holy grail, so to speak. Einstein, after he did his fantastic work on coming up with a new theory of gravity, wanted to extend that theory so that it included electricity and magnetism, and he didn't succeed in that. Because, in the opinion of most physicists, one of the reasons was that he didn't have the right mathematical structure and he didn't incorporate quantum mechanics. Now, he wasn't, let me be clear, he wasn't a fool, he had his reasons for doing it, but it wasn't going to work. Today, we have a structure in string theory and its successor, whereby all the basic forces of nature, the force that governs that govern the way atoms are built, and gravity as well, there is a candidate theory for bringing all those forces together, and that's what the excitement is about string theory. It may take a century to develop that theory, but I think we're on the right road.
Oh, so okay. So you give hope for new scientific breakthroughs to understand nature. In particular, and in your conclusion, you list 6 ideas that will be understood in the future, and I've taken some liberties here, and I wonder if you could talk a little about them.
All right.
Space and time are not fundamental.
Yep.
You touched on that. Yep.
Right, okay. If you look at the most advanced work that's done in quantum field theory and in string theory, it looks to most leading physicists that Einstein's idea of space and time, right, certainly the ones that we have in everyday world, simply are not sustainable. So space and time emerge from something more fundamental. Now that would be an astonishing thing if we had to revise those concepts. But now that is the consensus among leading physicists, and I for one expect them to be correct about that. I don't know. I'm not a clairvoyant. I can't be sure. Yeah. But it looks. All the signs are that we're going to need a radically new understanding of space and time.
Okay. Supersymmetry will be demonstrated. Could you describe what that is?
Supersymmetry is a fundamental symmetry of nature that's been conjectured by physicists. It's not been proved to be correct, right? Now, it hasn't shown up in the latest experiments at CERN, that's true, but I for one, have faith that it will show up in some guys sooner or later.
What is symmetrical with what?
Well, supersymmetry is a symmetry between different types of fundamental particle, and it is a method of looking at those particles and forming an overarching framework that theorists can work with. It's a beautiful framework, but as I say again, it hasn't shown up, much of the disappointment of many theorists, in the Large Hadron Collider at CERN.
Okay. Exotic subatomic particles are real.
Yeah, well, just let me give you one. When you're in high school, everyone knows you have north and south poles, right? And everyone knows that they always come together. Now, physicists believe that it is possible to have an isolated North Pole or an isolated South Pole, isolated magnetic poles. Now, that's been predicted long ago. In quantum theory, it was described by Paul Dirac, but now it's an essential part of our understanding of nature. And although those single magnetic poles haven't shown up, I, for one, and I think it's fair to say virtually all physicists expect them to show up sooner or later. That would be a real red letter day for physics.
How about quantum field theory will be simplified?
Well, quantum field theory is the theory that describes the way atoms are built at a fundamental level. You do calculations of quite simple things that experimenters check, and it's sometimes thousands of pages of calculations that eventually slim down or is reduced to something that you can write on your hand. Now, for that reason, physicists think there's something wrong here, we're missing something. And that's why some physicists believe, or in fact, quite a few physicists believe, that there's something wrong in our understanding of quantum field theory. And this is why I think they have a good point here, and that sitting in the studio in 20 years' time, we will have a different interpretation of quantum field theory, whereby we will understand how those thousands of pages collapse into one expression that you write on the palm of your hand.
Well, thank you very much. This is the book, The Universe Speaks in Numbers. Graham Farmelo is our guest today, and remember, watch locally.